All right, good morning, everybody. So on Monday, we started talking about iterative methods, and particularly on the motivation and the theory of convergence. So today, we are mostly going to be focusing on the implementation of these kind of iterative methods. As you see, in the theoretical analysis and derivation of the methods, we're really solving AX equal to B. But when you look at the implementation, the most elegant implementation of iterative methods for solving matrix equations involves actually no matrix at all. Well, you're still going to be deriving your implementation based on the matrix, but you actually have no matrix explicitly stored in the memory when you actually implement the solution of AX equal to B. All right, so for example, let's start with the Jacobi iteration. As I just remind people, Jacobi iteration is basically splitting A into A minus D plus D, right, times X equal to B. So we get two terms. One term is D times X. The other term is the off-diagonal A minus D times X equal to B. And the Jacobi iteration is nothing but moving just keeping D times X on the left-hand side and moving everything else to the right-hand side, where K is the iteration number, or some people call it a pseudo time step, right? It is essentially a iterative method is essentially something that time steps an unsteady equation towards a steady state, right? Okay, once you know that analogy, the similar things actually applies to even solving nonlinear equations. So there is also iterative methods for solving nonlinear equations that uses the same analogy. All right, so once you see that, let's think about how to implement this iteration. In particular, let's focus on the Poisson's equation. And the last time we looked at the 1 dimensions. So this time we'll look at the both 1 and 2 dimensions. We'll see the result is very similar. All right. So D times xk plus 1 is essentially, if you look at a particular grid point in 1 dimension, this is dii, okay, times xk plus 1 at the ith grid point would be equal to bi times A minus D times xk at grid point I, which we should focus on what it is. Because once we figured out what this is, we can just plug this into a algorithmic implementation, right? So what is A minus D times xk? If A has this tridiagonal structure, so A have 3 diagonals, well, A minus D is just taking away the diagonal, right? So instead of having a diagonal of whatever it is, it's just replacing the diagonals with 0. So that's basically A minus D. And in Poisson's equation, A minus D involves taking 2 neighboring grid points, multiply them with some number in the matrix, and add them together. So that is what A minus D is. So if you write it down, A minus D times xk at the grid point I is nothing but, okay, A of I minus 1 times xk at I minus 1 plus A at I plus 1 times I plus 1k. It's a weighted average of 2 neighboring grid points. It's a weighted average of the solution at the previous iteration over the 2 neighboring grid points, right? Okay, so for Poisson's equation, this dii in particular is what? It's minus 2 over delta x squared, right? This I minus 1 is actually 1 over delta x squared, and this is also 1 over delta x squared, right? So basically, this formula gives us implementation of what the Poisson's equation is. So it's basically minus 2 over delta x squared times xi at the k plus 1th iteration would be equal to bi and minus 1 over delta x squared times xi minus 1k plus xi plus 1k. So we know everything on the right hand side, and the left hand side can be just computed. All right, does it make sense? Any questions on this particular way of implementing the Poisson's equation? Yes?
Stability criteria or convergence criteria for this?
So there are multiple ways that you can guarantee convergence. So for example, if the matrix A is diagonally dominant, which means the absolute value of the diagonal is greater than the sum of the absolute values of all the off diagonals on the same row. Right, so that's one of the most common way of guaranteeing the Jacobi method to be convergent. But in practice, the Jacobi method actually converges for a wide variety of systems. Although there is even no theory of guaranteeing the method to converge. It converges. So, for example, for Poisson's equation, it is actually it is diagonally dominant in the sense that if you look at the diagonal, it's 2 over delta x squared. The sum of all the off diagonals is the same, right? So Jacobi method is guaranteed to not diverge in this case because the off diagonal adds up to exactly the same as the diagonal. But it also doesn't guarantee it'll converge. If the diagonal is strictly greater than the sum of the off diagonals, then the Jacobi method is guaranteed to converge. All right. Okay. So the same criterion applies to the Gauss-Seidel iterations.